So welcome everyone. I'm Theodore. I'm an analysis engineer at iPercept, and I'm really glad to have you here for session 3. For those of you who have been with us from the beginning, thank you for following the series. In today's session, we will look into the machine health down to component level from a mechanical point of view. So let's get started. Let me quickly walk you through what we'll cover today so you know where we're going. We'll start with subsystem anatomy, so the building blocks of a CNC machine. From there, we will go into failure and failure modes, what actually goes wrong inside each subsystem, why it happens, and how it develops over time. And in the final segment, we'll tie it all together by giving examples of how each failure and failure mode connects to a detectable acceleration pattern. We'll wrap up with 5 takeaways you can use immediately. And one more thing before we start, questions are very welcome, dropping them in the chat, and I will try to address them at the end. If we run out of time, I'll follow up by an email. So just a quick recap of where we have been. Session 1 made the case of why conventional vibration monitoring isn't enough for CNC machine, and session 2 showed you how the motion pattern method actually works. If you haven't seen those yet, you can find the recordings available on our website, and I strongly recommend them for you to see it. So what we're doing today. Today's session is about giving you the foundation that makes the detection meaningful. So when you understand the mechanism behind a failure, the pattern it produces in the data, then it stops being a curiosity and starts being a verdict. So segment 1, we will look into the anatomy of CNC subsystems as it is the foundation for everything else. So from this segment, here's what I want you to take away. A shared mental model of what's actually inside a CNC machine and how each part contributes to the motion. Every CNC machine, regardless of make or model, is built around the same 3 primary subsystems, so linear axis, spindles, and rotary axis. These 3 subsystems are in some way mechanically independent, but also in some other ways they can be seen as dynamically coupled. So, for example, a failing coupling in a linear axis loads the ball screw bearings, or a spindle bearing defect that can transmit vibration into the rotary axis of the spindle head. iPercept's component level analysis through the motion pattern method isolates each subsystem signature to these interactions and can be tracked. So let's go through each subsystem in detail, starting, of course, with linear axis. So ball screw is one of the key components in linear axis. So the quality of the ball screw assembly depends almost entirely on preload. It's the most critical parameter for every ball screw as it removes free play between balls and raceways, giving the axis stiffness and, of course, the bidirectional positional accuracy. Without it, backlash will be present at every reversal. It can be set by oversized balls, interference fit, or double nut offset. The important thing to remember here is that preload is not a binary state. It degrades continuously and silently at each load cycle, causing microplastic deformation at ball raceway contact, reducing slowly the interference fit. So every component in the assembly affects how preload is set and how and why it degrades over time under cyclic loading. Lubrication and sealing are the 2 things that slow this process down. If the recirculation path gets contaminated or if the lubricant film breaks down, wear accelerates. And support bearings, whether they are fixed or floating, are part of the same system. The fixed end carries axial thrust and radial loads, while the floating end allows for thermal expansion of the shaft. Wear here adds axial play that compounds directly with any preload loss in the nut. Typical type for support bearings can be deep groove ball bearings, cylindrical rollers, or hybrid. On the drive side, the servo motor provides torque and position feedback. The coupling connects it to the ball screw, and the type of coupling matters here. A soft coupling, for example, absorbs misalignment but allows motor torque ripple through to the screw shaft. A stiff coupling transmits misalignment loads into the bearings. So when the coupling inserts hardens or cracks, it loses its damping function entirely. We'll come back to that later in segment 2. Guideways are the other half of the linear axis. They carry the radial and moment loads that the ball screw doesn't. The rail profile, carriage geometry, and rolling element type and preload determine the load capacity stiffness. So rolling elements, balls, or rollers circulate inside each carrier block. The key vulnerability here is the recirculation path. If contaminations gets in swarf or debris from machining, it acts as an abrasive inside the carriage. And once the seal integrity is lost, that contamination-driven wear can be orders of magnitude faster than normal fatigue wear. This is why seals and scrapers are not a minor detail, but they are primary wear protection mechanism in this case. One thing that is worth noting is that guy-wire wear is the most gradual of all linear axis failures. It accumulates slowly over a large contact surface. This means it often goes undetected for a long time. Machine orientation also matters here, so horizontal versus vertical orientation changes how gravity loads the carriage and of course the ball screw. So gantry machine versus column machines have different structural stiffness profiles and same components, different wear pattern depending on how they are configured. The spindle is where the power is concentrated. Spindle bearing failure is arguably the most expensive failure you can have on a CNC machine in terms of repair cost and lead time. Spindle bearings, whether angular contact or cylindrical roller or hybrid ceramic, are arranged to carry both radial and axial load simultaneously. The arrangement and preload setting determine the stiffness and accuracy of the spindle. And here's the tricky part. Preload is not static. The spindle expands actually as it warms up, which shifts bearing preload. On machines without active thermal compensation, the preload at cold start can be different from the preload at operating temperature. The lubrication type makes also a practical difference. So grease lubrication is simple and maintenance-free and is suitable for spindles up to 12,000 RPM. Above that, typically oil mist systems provide a continuous fresh lubrication supply, enabling speeds up to 40,000 RPM. So each produces different vibration pattern. The tooling interface, whether it's an HSK, a CAPTA, or a BT, is easy to overlook. But interface wear or contamination reduces dynamic stiffness and shows up as a broadband noise at the spindle nose. Usually it's the first symptom of a problem that gets attributed elsewhere. The bottom line on spindle bearings, high speed, high load, and virtually impossible to inspect without disassembly. The drive configuration of the spindle tells you a lot about what the vibration pattern will look like, and therefore what you need to filter out when you're doing the analysis. At one end of the spectrum, you have direct drives and integrated motor spindles. The motor is either directly coupled to the shaft or built into it. No intermediate elements, no transmission components, just clean rotation. This produces the simplest vibration patterns, which makes bearing defects the easiest to isolate. Belt-driven spindles are a different picture. Belt tension, pulley wear, and belt fatigue all introduce additional periodic frequencies. So overtension, for example, puts excessive radial load on the spindle bearings, which can accelerate bearing fatigue. Undertension can cause belt slip, which shows us amplitude modulation at the belt mesh frequency. Worn pulleys add their own frequency contributions. So in short, belt drives are a very rich and noisy diagnostic environment. Gearbox-driven spindles are the most complex. They are found in heavy-duty machining centers where high torque requirements are necessary. Gearbox adds mesh frequencies and sidebands that can overlay the bearing frequencies. Lubrication is critical here, so not just to prevent metal-to-metal contact between gear teeth, but because particle contamination from gear wear debris reduces lubrication film strength and can accelerate both bearing and gear surface degradation. Rotary axes are the most mechanically diverse of the three subsystems. For example, a worm-driven A-axis and a direct drive C-axis don't have so many commonalities in terms of failure mode profile and detection strategy. So let's start with the bearings. Cross-roller bearings, which you can mostly find on rotary tables, have cylindrical rollers arranged in an alternating 90-degree V-groove raceway. This geometry lets a single bearing carry simultaneously thrust, radial, and moment loads. Angular contact bearings are the other common type, which we frequently see in rotary heads, where stiffness is a priority. One thing that makes rotary table bearings diagnostically interesting is their diameter, which can often span up to 800 millimeters for very large rotary tables. Because of that large diameter, the patterns that are produced and the frequencies can be very low, sometimes under 10 Hertz. The clamping mechanism is another component worth calling out. Hydraulic or mechanical clamping applies a control preload for indexing, and the repeated clamping cycles create fatigue loading on the bearing. Over time, wear and failure here can make the axis mechanically inoperable, not just inaccurate. Finally, the sealing. Rotary axis and especially rotary tables operate right next to coolant and chips. So seal integrity is a primary line of defense against contamination into these large bearing diameters. This slide here covers the three main drive mechanisms you will encounter in rotary axis, and they behave very differently from each other. Worm and wheel drives deliver high reduction ratios in a compact package, which is why they're widely used, but they come with inherent backlash that grows with wear. The worm wheel contact surface is the primary wear site, where lubrication at the interface is critical because it's a sliding dominating contact. Torque motor direct drives sit on the other end of the spectrum, as we already said. The motor drives the axis directly with no mechanical reduction, as we have seen in the spindles, which means maximum stiffness and zero backlash. Belt drives for rotary axis offer low inertia and low friction. Also, they have minimal backlash provided that the belt tension is maintained properly. The drive characteristic here is similar to what we have seen in spindle and belt drives. I would like to make one note here. Cam roller drives and rack and pinion drives are also existing in rotary axis drive options, but we will not cover them in detail today. So the principles we have discussed so far for the three mechanisms above generally transfer to the different systems. So far we covered the anatomy. Now comes the part that tells you what to watch for. In this segment, we will go through the most common failures or failure modes across the three subsystems. So not just what fails, but we will try to look also into the mechanism behind it. So why it starts, how it progresses, and what changes it produces. The word I want you to remember here is mechanism. So every fault or failure has an underlying mechanism. When you understand the mechanism, the data stops looking like noise and starts looking like information. So starting with a ball screw assembly, preload loss is the headline failure here and the hardest to catch manually. It happens gradually through microplastic deformation at the ball raceway contact with every load cycle. So there is no a single event or noise or visible damage. So it just slowly grows into backlash. The first detectable sign in the data is a slight increase in reversal error in the linear axis test. Spalling is different in character. It's more abrupt. Subsurface fatigue cracks propagate to the surface and material flakes off, creating pits in the raceway. If the pit is on the ball screw shaft, every ball that passes over it generates a periodic impact at the same travel position. So it will be visible as a position defect in the linear test. If the spalling is in the nut raceways or in the rolling elements, the signal repeats throughout the entire travel stroke. Contamination from swarf or grinding dust and chips acts as an abrasive inside the recirculation path. It produces a continuous broadband noise floor across the entire linear path, so it's not a position specific. That broadband pattern is actually a useful diagnostic clue here, as it tells you that contamination is present. Lubrication failure is similar in signature to contamination, so we have a broadband noise rise across the full stroke. The key difference here is the root cause, so starvation from blocked nipples or degraded lubricant, or sometimes over lubrication that flushes out the affected lubricant film. So both drive metal-to-metal contact and accelerate race wear. Finally, support bearing failure. These end bearings degrade under axial thrust cycling, adding axial play that compounds directly with any preload loss already present in the nut. The signature and the pattern here includes bearing defect frequencies, which makes it identifiable as distinct from the ball screw shaft itself. Guideway failures have some of the most visually invisible failures. You can't see anything wrong with the carriage until the play is large enough to feel it, and by that point that's already degraded. Preload loss is the primary long-term failure mode. Rolling elements were under continuous contact, losing in diameter and reducing the interference fit that creates stiffness. The first kinematic expression here is play perpendicular to the direction of motion, not in the direction of travel, which is why it often doesn't show as positioning error until it's quite advanced. Monitoring can catch it much earlier as a rise in vibration at carriers defect frequencies during the linear test. Surface fatigue spalling follows the same physics as the ball screw. Subsurface cracks propagate under Hertzian contact stress, material flakes off, and rolling element passing over the resulting pit generate periodic impulse at the fixed position in the linear axis test. The diagnostic signature here is similar to the ball screw, but the detection direction hinges to the guideway and not the ball screw. Contamination and abrasive wear produce broadband noise across the full stroke, again, similar to the ball screw contamination. The distinguishing feature here is that this noise is associated with direction lateral to the direction of travel. Block lubrication port compound this, so without fresh lubricant replenishment, the abrasive particles already in the system are flushed out and wear accelerates. Brinelling is a special case. It can be caused by a single event rather than gradual fatigue. A collision or a shock load or overly aggressive motion, any of these can permanently indent the raceway. The result is a periodic vibration at carriage ball pass frequency, or in severe cases, crack initiation at the indentation site. Before we go into specific motor and coupling failures in this slide, I will take a small pause and discuss about something that applies to everything in this segment. So the cascading effect. To give you an example of what I mean by that, think of a coupling installed with a slight misalignment 3 years ago or 4 years ago, and which may have worn the support bearings due to asymmetric loading, to the point where the screw run out is significant, which is now an accelerating ball screw nut wear. So not really replacing the ball screw in this case might solve the problem, but at what cost, right? So without component level monitoring, the operator sees positioning error and replaces the entire ball screw assembly without finding the root cause. Now, let's go back to the motor and coupling failures specifically. Two common root causes that create motor bearing wear in a servo motor are excessive radial load from coupling misalignment, which loads the motor shaft laterally, and electrical discharge erosion. In this case, current passes through the bearing shaft, causing pitting and flattening on the races. Winding insulation breakdown is a thermal story. Sustained overload or undersized motor selection stresses the dielectric insulation, and voltage spikes from drive switching accelerate that breakdown. The diagnostic pattern here is more of a periodic radial force at twice the electrical frequency caused by the imbalanced magnetic field from partial insulation failure. Encoder failures of the motor are less common but consequential. So contamination or mechanical shock can compromise the position feedback signal, and when that happens, the motor loses accurate positional reference without necessarily that triggering an obvious alarm. On the coupling side, misalignment is one of the failures. Whether angular or parallel, misalignment means that the motor and ball screw center lines are not coaxial, which loads the bearings on both sides as a secondary effect. So the cascading effect. They can appear in the data as vibration peaks at motor first and second harmonics, symmetric in both travel direction. When the coupling insert hardens or cracks, it loses its damping function, and the motor torque ripple now transmits directly to the ball screw shaft. In the next slides, we will also see other types of drivetrains, which can be found in all three primary subsystems. But for now, we're moving on to the spindle bearings. As we said earlier, spindle bearings are the most important component to monitor proactively, and the reason is simple. You cannot inspect them without disassembly. There is no visual check or quick manual test to do. So weekly measurement is one of the practical ways to know what's happening here. So this is where iPercept comes in. The 4 failure modes here have very different diagnostic characters, and telling them apart is what makes the difference between a correct diagnosis and a wrong one. Abrasive wear from particular contamination is the most gradual. So preload slowly drops, clearance increases, and the runout can grow. In the data, it shows as uniform broadband noise, which is increasing across all spindle speeds, so it's not associated with a particular frequency. Spalling, on the other hand, is periodic. Cyclic Hertzian contact stress initiates subsurface fatigue cracks, material flakes off, and rolling elements passing over the created pit are generating impulses at the ball pass frequency of the inner or outer race. Sidebands around the running frequency might grow as the pit becomes bigger. If you're not monitoring and rely only on machining quality, usually the first sign is often chatter on the workpiece surface. Brinelling is also periodic, but it's caused by an event, so it's not a gradual fatigue. A crash or a hard stop at the same spindle position repeatedly, or excessive vibration at standstill, so any of this can permanently indent the raceway. The ball pass impulse appears immediately after the event and doesn't grow the way spalling does. Corrosion fatigue is the most insidious. So coolant ingress corrodes and pits the bearing surface, and those pits become crack starters under the cyclic loading. So what begins as a corrosion problem becomes a fatigue problem. So these two mechanisms accelerate each other, and the combined failure progression is faster than either would be alone. So worn seals, wrong coolant pH, or inadequate rust inhibition. So they're all common causes that could prevent the corrosion fatigue. In this slide, we cover drivetrains that appear across all three primary subsystems. So gearboxes in spindles and rotary axis, for example, or belt drives that are present in both spindles, rotary axis, and linear axis. So the failures we're about to discuss apply regardless of which subsystem the drive serves. We start with gearboxes. Gear tooth wear is the primary long-term failure mode. So cyclic contact loading at the tooth faces causes pitting and spalling, accelerated by vibration starvation, by lubrication starvation or contamination, or misalignment causing uneven load distribution. The diagnostic pattern here is an increase in gear mesh frequency amplitude with sidebands growing around it. So more sidebands over time indicates the wear is propagating, which is a useful trend to track over time. Gearbox bearing defects follow the same spalling and abrasive wear mechanism we have already seen. The specific risk here in the gearbox is that the gear wear debris contaminates the lubricant, which then circulates and acts as an abrasive against the bearing races. Lubrication oil analysis can be a complementary monitoring tool here. Backlash increase is the output level fault. So adhesive and abrasive wear of the tooth flanks widens the clearance between the meshing teeth. So in linear and rotary axis, this produces following error and lost motion at the reversal points. In spindles, on the other hand, it degrades surface quality. So sometimes backlash compensation can be set incorrectly after maintenance, masking the underlying wear, so which is another argument for monitoring rather than relying purely on the controller feedback. On the belt drive side, belt wear and tension are the primary concern. So over time, the cyclic tensile and bending stress causes fatigue cracks and tooth wear, especially under contamination conditions or poly misalignment. So tension changes so as amplitude modulation at the belt mesh frequency. So under tension of the belt causes belt sleep. Over tension can cause load in the spindle bearing. Pull imbalance is relatively easy to identify by looking for increased vibrations at pulley shaft speed without harmonics or sidebands. Finally, tooth flank wear is less pronounced, so you're looking for sideband growth trends over time rather than a single threshold event. Next, we move on to rotary axis failures, which are a combination of slow development, high repair cost, and near zero external visibility. So that's a very, very good case for proactive monitoring in one sentence. So where iPercept comes in. Starting with a bearing, spalling on large diameter cross-rolling bearings follows the same Hergen fatigue mechanism we have seen throughout this session. The key difference here is that the defect frequencies are very low, so it can be often less than 10 Hertz because the circumferential speed is slow despite the large diameter. So these frequencies sit in a challenging part of the spectrum to monitor, but the amplitude growth as the degradation progresses is clear and trackable. Contamination ingress is the other major bearing failure driver. Chips and coolant bypassing contact seals introduce abrasive particles onto the large rolling surfaces. And unlike smaller bearings, there is a lot of surface area to damage here. So seal condition is the primary preventing measure here. Axial play develops as bearing preload loss and raceway wear, reducing the contact interface. It becomes measurable as positional error when cutting forces load the table axially. In our test cycle data, it can appear as an oscillation at the table reversal, which is a distinct pattern that you can track over time. Now for the worm drive failure modes, and these are particularly important because worm wheel contact is a sliding dominated interface, which means the lubrication film failure is not a secondary concern, but it's the primary one. So in tooth pitting, subsurface cracks propagate under the cyclic Hergen stress at the worm to wheel contact interface. So high sliding velocity makes this more aggressive than typical gear contact. Diagnostically, it shows us sidebands growing around worm mesh frequency. Tooth scaffing is the most time-critical failure in a worm drive. So when the lubricant film starts breaking down under load and speed, you get metal transfer and surface tearing between the steel worm and the bronze wheel. This can progress from detectable to destructive quite fast. So a rising noise floor at the mesh frequency is a warning sign. Finally, backlash increase ties all of this together. So as tooth wear progresses, worm wheel backlash grows and shows up as distortion at the axis reversal in our test cycle. So the final segment is short. So far, we have covered the anatomy of the subsystems and the failures and failure modes. And in the next session, in the next segment, we will see how certain failure maps directly to detectable acceleration signature. So iPercept motion pattern method is where anatomy and failure modes and failures connect. So in this table, we have a synthesis of some of the things we have covered today. So every row connects a failure or a failure mode we have seen to the acceleration signature or a pattern. So for example, bolt screw preload loss shows as a reversal impulse at the position. Bolt screw spalling shows as periodic impulse at the bolt pass frequency. Guide wear shows as high frequency vibration at carriers defect frequencies, or the spindle bearing spalling shows as harmonics of the bolt pass defect frequencies, and so on and so forth. So the logic here is consistent. So every failure or failure mode changes the machine's kinematic behavior in a predictable physics grounded way. So the pattern that we see is not noise, it's the mechanism expressing itself in the acceleration data. So looking back to session 2, this table gives you a more complete picture. So what goes wrong, what it looks like in the data, and how iPercept detects it. And in this slide, we cover what this monitoring is all about. Once a fault becomes detectable, the escalation rate is determined by the failure mechanism itself and not by when you happen to check. So some failure modes give you months in observable states to act upon, while others might progress much faster. So it can move from observable to critical in weeks or even days. And this is consistently shown in our data. So the majority of accelerated stage degradations that might have led to unplanned downtime were preceded by an observable stage. So here is the value of continuous monitoring. It's not just about detecting the faults, it's about giving you and your maintenance team the window to act before secondary wear or damage starts to kick in. So let me close with 5 things I want you to carry out from today's session. So first, anatomy is universal, as we have seen. So every CNC metal working machine, regardless of make or model, is built around the same 3 primary subsystems. Once you know the building blocks, you can navigate any machine. Second, failure modes are specific. So each subsystem component has its own failure and failure mode. So the list is large, but it's finite, so you can go back and learn some of them. Third, every failure changes the kinematic behavior in a predictable way. That's not coincidence, it's physics. So the mechanism behind the failure determines what pattern it produces. This is what makes diagnosis possible. Fourth, that's why the motion pattern method works. It's a fault, so it's not noise to be filtered out. So the information with a known shape and pattern. So if you know the mechanism, you know where to look and how to detect it. And fifth, degradation is a structured process. So understanding that structure is what turns reactive maintenance into a planned intervention. We have 2 more sessions coming in the series, and if you found today's session useful, I think you will enjoy both of them. Session 4 is a practical guide on how to implement this motion pattern method and iPercept solution to your CNC fleet without a large ISD project. And session 5 covers mostly operational monitoring, so collision tracking, utilization, process health, and load intensity. For the next webinar series to follow, follow us on LinkedIn to receive notifications, or the existing participants will also be notified by email. So follow us to be updated. Thank you all for spending 30 minutes with us today. I will check if there are any questions now. And if we don't have enough time to answer them all, I will answer and reply by email to all of you. Thank you very much. Okay, we have a question from class. If runout can be detected in a spindle and how it should show up in the data. Yes, we can detect that, and typically runout will be present, or the pattern that we will see, it's increase in the frequencies of the spindle rotation, especially the first, second. Okay, thank you very much, and have a nice rest of the day.